Alright, nerds. So we're going to look at the Haber-Bosch process today. And essentially, this is where we get most of our industrially used ammonia. Alright, so these are our dot points we're going to address today. We're going to identify what it's made from. We're going to describe the synthesis. We're going to describe how it occurs. We're going to describe it as a reversible reaction. And we're also going to identify that it's an exothermic reaction. So by the end, at the very least, you should be able to explain the details of the reaction to produce ammonia, and you want to be able to explain it and the impact of Le Chatelier's principle on the process. Okay, so we need to re-go over Le Chatelier's principle one more time. In particular, a decrease in concentration of substance. So if we decrease the concentration of a substance, it will move towards the side that substance comes from. If we increase the pressure of a system, it will move towards the side with fewer gas particles. And if we increase the temperature, it will move away from the heat or energy side, which is the exothermic side of the reaction. All right. So here's our reaction. Now, we're calling it Haber-Bosch because it was actually the process was produced by two German scientists, Fritz Haber and Carl Bosch, as in the Bosch Chemicals company. So this is a reverse reaction. We do it on our PowerPoints like this, that reaches equilibrium. Now, the equilibrium in standard lab conditions favors the reactant side. This is why ammonia and hydrogen, just at room temperature, won't naturally just form a bunch of ammonia in the air. All right, so we started to freak out for a little bit there. All right, so it's exothermic, and all this means essentially is that the bonds of the reactants hold more energy than the bonds of the products. Okay, so the intramolecular bonds here and here have more energy than the intramolecular bonds right here. So we also need to be aware of the boiling points while we're at it. So this is the details of it. First off, hydrogen's boiling point is at about minus 255. Nitrogen's boiling point is at minus 195.8 or minus 196. Ammonia's boiling point is at minus 33 degrees. So this one, boiling point is where it turns from a liquid to a gas, but it's also where it turns from a gas to a liquid. So this one turns from a gas to a liquid at this temperature, and these ones turn from a gas to a liquid at this and here. All right, so let's have a quick look at it. We have 3 gaseous particles of hydrogen, 1 gaseous molecule of nitrogen. We add those together, and this gives us 2 gaseous molecules of ammonia. Okay, so this is 4 gaseous molecules, 2 gaseous molecules. So if we increase the pressure, just by looking at it right now, if we increase the pressure, it will move towards the side with less gaseous molecules. If we increase the temperature, it will move to this side because it's an exothermic reaction. All right, so what is the Haber-Bosch process? First off, it is this reaction right here. You have a nitrogen plus 3 hydrogens over heat, pressure, and a catalyst. All 3 of those are essential. They give you ammonia. Here we have it is minus 92 kilojoules per mole, which means it is an exothermic reaction. All right. So basically, gas enters the compressor over here. We'll have a better diagram. This is a good diagram for you to draw. The next diagram is more of just a detailed diagram. So the gas enters. So what we're going to do is we're going to list off each step, and then we're going to explain what the effects of that step are. So up here, the gases are all pumped in, and they enter a compressor. All right. The compressor increases the pressure. All right. So the pressure does 2 things. It reacts to break, or it acts to break the molecular bonds. So your N2s go from N2s to just Ns. H2s go from H2 to just H atoms. It does that. And also it increases the pressure, and therefore the reaction will try to relieve the Le Chatelier's principle means it will try to relieve the pressure and move towards the side with less gas. This will maximize our yield of ammonia. All right. So the mixture is then heated to about 500 degrees Celsius. Now, as the reaction is exothermic, it will move this way to the left. So you see that we have to balance it. Now, it will come into contact with the iron catalyst. During this stage, only about 10%, and this is where the reaction occurs, 10% will turn from gaseous nitrogen and hydrogen to ammonia. So about 10% of it will turn to ammonia, and then it will hit this area here, which we will call a condenser. And as it enters the condenser, the ammonia, so it all cools down to about minus 33 degrees, possibly could go a bit cooler. And once it hits minus 33 degrees, the ammonia condenses from a gas to a liquid and comes out of solution. So it comes out, and there we go. And the rest of the gases are recycled around. Now, we've actually taken out of this system, we've taken the ammonia out. This reduces the concentration of ammonia. Therefore, the reaction, as this has been reduced, the equilibrium will shift towards this side. Once again, maximizing our yield of ammonia. So the remaining reactants, which go back up here, they hit the compressor again, are recycled until enough ammonia is created. That's the Haber-Bosch process. Now here's a slightly more detailed diagram. So the gases are fed in through here, they come down and they are compressed. So they are heated up. They heat up through this coil, they hit the catalyst bed, they go through the reaction. You now have the three gases mixing here, okay? They travel through, they start to cool down a little bit. They cool down a little bit and enter the condenser, in which point they cool down to the boiling point of the ammonia, which will then come out as a liquid. This is then, the remaining gases then recycled back up and around and in. So they recycle, so they come around this way and back up through the heat exchanger where they warm up again, come back in here, and off we go. So why so hot? It seems like a real negative thing to have it, doesn't it? So we're talking about a reaction that would never ever happen at room temperature, okay? When we heat it up, we increase the rate of collisions. This reaction would never ever happen at room temperature. Therefore, it gets heated up and the reaction occurs quicker. So a higher rate of reaction is vital to industrial production. It's necessary. The higher temperature also increases the rate that the gas moves through the pipes and equipment, so it also makes it a more efficient one. So as we heat up the reaction, the rate of reaction increases. The speed that it moves through the system is also faster, yet we have the downside here of it reducing the yield. Okay, and we see that here, right? So here is what it would look like with ammonia, the production of ammonia. It's an exothermic reaction. This would be our energy profile. Now, as an exothermic reaction, the high temperatures are going to decrease the yield. The way around this is you actually remove the ammonia before it has a chance to go back into, to convert across that barrier, back into nitrogen and hydrogen. So the Haber-Bosch is actually a very delicate balancing act. It's a trade-off, and this means we need to monitor and manage this reaction. We need to monitor the percentages of what's going in and what's coming out. So here's a very quick look. We maximize the yield by removal of NH3. We increase the pressure and we lower temperature. Now, 500 degrees is not actually that hot a temperature to run an industrial plant. It's a moderate temperature. It could be hotter. If it was hotter, it would happen much, much faster. But at the same time, you would also lower your yield. So it's a compromise. And that's it. That's the Haber process. It's actually pretty simple. And we'll see you in class.